Can you truly move your hand without your brain's permission? Well, consider this for a moment. Right now, if you decide to tap your fingers against the table, the action feels instantaneous. The thought becomes the deed in a flash. You feel the cool, solid surface of the wood at the exact moment you see your fingers make contact. This seamless connection, this beautiful and intricate link between sensing the world and acting upon it, is the quiet miracle of neural control and coordination. It is an unseen conductor, orchestrating a symphony of electrical signals, chemical signals that allow us to navigate our world. In the following exploration, we shall demystify this complex process, breaking it down into its fundamental, understandable components. We will journey deep into the architecture of the nervous system, revealing how messages are born, how they travel at incredible speeds, and how they result in every single motion we make. We will also pause to witness a simple, everyday story that beautifully illustrates this entire system in action, making the abstract concepts tangible and relatable. By the end of our journey, you will not only understand the science, but also appreciate the profound elegance of the biological machinery that makes you, you. Let us begin this fascinating exploration into the body's internal communication network. This system is not just about grand gestures or athletic feats. It governs the subtle, unconscious processes that sustain us, the steady rhythm of your heart, the unconscious expansion and contraction of your lungs as you breathe, the way your eyes adjust to changing light. All are testaments to the constant, vigilant work of neural control. It is a system of immense complexity, yet its principles can be understood. We will peel back the layers, starting with the broadest view and gradually focusing on the microscopic details that make it all possible. The promise is not just knowledge, but a newfound appreciation for the silent, tireless work happening within you at every moment of every day. Our exploration is designed to be a clear and steady guide. There will be no confusing jargon left unexplained, no complex idea left unexplored. Think of this as a documentary for the mind, where each section unveils a new aspect of this incredible biological story. We will start with the big picture, defining what neural control and coordination truly mean for a living organism. Then, we will zoom in, discovering the specialized parts and their unique roles. The journey is structured to ensure that each new piece of information fits perfectly with the last, creating a solid foundation of understanding. So, prepare to uncover the secrets of your body's most sophisticated system. Now, let us establish what we mean by neural control and coordination. At its core, this is the body's master system for receiving information, processing it, and initiating an appropriate response. It is the intricate network that allows an organism to perceive its environment, to think, to feel, and to move with purpose. A vast collection of specialized cells and organs must work in perfect harmony to achieve this. Imagine an immense and highly efficient corporation. At the top, you have the chief executive, the brain, which makes the most critical decisions. Supporting it is a primary communication line, the spinal cord, which acts as a superhighway for information traveling to and from the central office. Branching out from this highway are countless smaller pathways, the nerves, which are like the local couriers delivering messages to every corner of the body. And finally, you have the workers on the ground, the muscles and organs, which carry out the instructions they receive. When all these components function as a single, cohesive unit, the body can perform tasks as simple as blinking and as complex as playing a musical instrument. This integration is the essence of coordination. It is the difference between a random collection of parts and a living, breathing, and responsive being. It is the biological framework that underpins our entire existence and our interaction with the world around us. This system is constantly active, a silent hum of activity that never ceases. Even in the deepest sleep, your neural network is hard at work, regulating your heartbeat, managing your breathing, and consolidating the memories of the day. It processes a torrent of sensory data from both the outside world and your internal environment. The feeling of the clothes on your skin, the ambient temperature of the room, the faint sound of traffic outside. The beauty of this system lies in its dual nature. It is both a centralized and a distributed network. The brain acts as the central command, responsible for conscious thought, planning, and voluntary actions. However, some responses are so urgent that they cannot wait for a decision from the top. For these situations, the system has built-in shortcuts, local command posts within the spinal cord that can issue immediate orders to protect the body from harm. This blend of deliberate, thoughtful control and lightning-fast automatic reflexes gives us the versatility to handle an enormous range of situations, from solving a complex puzzle to snatching our hand away from a hot stove. It is a masterpiece of biological engineering. Next, we must examine the fundamental structure of this incredible network. The nervous system is broadly divided into two principal parts, each with a distinct and vital role. The first is the central nervous system, or CNS. This is the processing core, the biological equivalent of a supercomputer's central processing unit. The CNS consists of two main components: the brain, which is the seat of consciousness and complex decision-making, and the spinal cord, a thick bundle of nerves that extends from the base of the brain down the back. The CNS is where information is analyzed, interpreted, and where commands are formulated. It is the ultimate authority in the body's chain of command. The second major division is the peripheral nervous system, or PNS. If the CNS is the command center, the PNS is the vast network of communication lines that connects the center to the entire periphery of the body. It is composed of all the nerves that branch out from the brain and spinal cord, reaching every organ, muscle, and patch of skin. The PNS itself has two primary functions, or jobs, that it performs relentlessly. It is a two-way street, constantly ferrying information in both directions. Understanding these two pathways is crucial to understanding how we interact with our environment and how our brain exerts its control over our physical form. The first job of the peripheral nervous system is the sensory function. This involves collecting information from the body's sense organs and transmitting it inward to the central nervous system. Nerves dedicated to this task are like reporters in the field, gathering intelligence from the front lines. When your skin feels the warmth of the sun, specialized receptors generate a signal. That signal is then carried by a sensory nerve up through the PNS, into the spinal cord, and finally to the brain for interpretation. The same process occurs for everything you see, hear, taste, and smell. It is a constant stream of data about the external world flowing into the command center. Now let us zoom in even further to the microscopic level. The fundamental unit of the nervous system is the neuron, also called a nerve cell. It is designed for one purpose: high-speed communication. A typical neuron has three main parts: cell body, dendrites, axon. Cell body, or soma, contains the nucleus and cellular machinery. Dendrites, short tree-like branches that receive messages. Dendrites act like antennae. More dendrites, more input. Axon, a single long branch that sends messages away. Sends messages to other neurons. Sends messages to muscles. Sends messages to glands. Signals travel with astonishing speed. Transmission is a two-step electrochemical process. Within a neuron, the signal is an electrical impulse traveling down the axon. At the axon terminal, it meets a tiny gap called the synapse. The signal cannot cross electrically. Arrival triggers release of neurotransmitter chemicals. Neurotransmitters bridge the synaptic gap. They diffuse across and bind to receptors on the next neuron's dendrites. Binding triggers a new electrical impulse in the receiving cell. A chain reaction, an electrical baton passed to a chemical runner, then back to electricity. This lets information travel from your toe to your brain in a fraction of a second. Repeated billions of times, this forms the basis of thought, sensation, and action. Next, we explore one of the most elegant and vital functions of the nervous system, the reflex. A reflex is a rapid, involuntary, and predictable response to a stimulus. It is an action you perform without conscious thought, a built-in safety mechanism that protects the body from harm. A classic example is the immediate withdrawal of your hand after touching a painfully hot object. You do not stop to think, this object is hot. I should probably move my hand. The action happens before your brain has even had a chance to consciously register the pain. This incredible speed is made possible by a special neural pathway known as the reflex arc. The reflex arc is a neural shortcut. Instead of sending the sensory signal all the way up to the brain for a decision, it takes a detour through the spinal cord, which acts as a local relay center to initiate an immediate motor response. This arc consists of 5 essential components working in a precise sequence. The first is the receptor, a specialized nerve ending in the skin or other organ that senses the initial stimulus, such as intense heat or sharp pain. The receptor's job is simply to detect a threat and sound the alarm by generating a nerve impulse. This is the very beginning of the protective cascade. Once the alarm is sounded, the second component, a sensory neuron, takes over. This neuron's axon extends from the receptor all the way to the spinal cord, carrying the urgent message of danger. Upon arriving at the spinal cord, the third component, the signal is passed, often through a small intermediary neuron called an interneuron, directly to a motor neuron. The spinal cord, in this context, does not need to consult the brain. It is empowered to act on its own, functioning as a rapid response command post. This is the crucial step that makes the reflex so incredibly fast, bypassing the longer route to the brain. The fourth component is the motor neuron. Having received the command from the spinal cord, this neuron carries the action signal out to the relevant part of the body. Its axon extends from the spinal cord to the muscle that needs to act. Finally, the fifth component is the effector, which is the muscle or gland that carries out the response. In our example, the effector is the muscle in your arm, which receives the signal from the motor neuron and contracts forcefully, pulling your hand away from the hot object. Only after this action is complete does a parallel signal continue its journey to the brain, informing it of what just happened. That is why the sensation of pain often registers a split second after you have already moved. Now we return to the command center itself, the brain, to understand how its different regions contribute to control and coordination. The brain is not a single uniform mass. It is a collection of highly specialized areas. Each is responsible for different tasks. The largest and most prominent part is the cerebrum. This is the center of higher-order thinking, responsible for conscious thought, memory, language, and the initiation of all voluntary movement. When you decide to pick up a book, that intention originates in your cerebrum. It is also where sensory information from your eyes, ears, and skin is processed and understood, giving you a conscious perception of the world. Tucked beneath the back of the cerebrum is a smaller but critically important structure called the cerebellum. Its name means little brain, and it is the absolute master of coordination. While the cerebrum issues the command to move, the cerebellum ensures the movement is smooth, balanced, and accurate. It acts as a quality control center, constantly comparing intended movement from the cerebrum with the actual movement. It receives real-time sensory feedback about your body's position and motion, and if it detects a mismatch, it sends corrective signals to fine-tune the action. This lets you walk in a straight line without toppling over, reach for a glass of water without knocking it over, and sign your name with a steady hand. It refines raw motor commands into graceful, coordinated actions. Damage to the cerebellum can cause jerky, uncoordinated movements, and severe loss of balance. It is the silent partner to the cerebrum, translating intention into skillful execution. Without the cerebellum, simple physical tasks become extraordinarily difficult. Connecting the cerebrum and cerebellum to the spinal cord is the brainstem. This is the most ancient and fundamental part of the brain, responsible for regulating essential life-sustaining functions below conscious awareness. The brainstem controls breathing rate, heart rate, blood pressure, and sleep-wake cycles. It is the vigilant guardian that keeps the body's basic machinery running, awake, or asleep. Together, these regions, the thinking cerebrum, the coordinating cerebellum, and the life-sustaining brainstem, work with the spinal cord to produce the full spectrum of human behavior, from the most basic reflexes to the most complex creative endeavors. To see how all these pieces come together, let us consider a simple, everyday story, the act of catching a ball. Imagine you are standing in a park on a sunny afternoon. A friend tosses a ball toward you. In the few seconds it takes for the ball to travel through the air, your nervous system performs a breathtakingly complex series of calculations and actions. It all begins with your eyes. As you watch the ball's trajectory, the retinas in your eyes capture the image, packed with light-sensitive receptor cells. This visual information is instantly converted into electrical signals, a stream of data describing the ball's position, size, speed. These signals travel from your eyes along the optic nerves and are routed to the visual processing centers in the back of your cerebrum. Here, the brain interprets the raw data, calculating the ball's path and predicting where it will be in the next moment. Based on this prediction, the motor cortex formulates a plan of action. It generates a series of commands. Extend your arms, open your hands, prepare to absorb the impact. This initial plan is like a rough draft, a general instruction for what needs to happen. It is a conscious decision to engage and intercept the approaching object. Now the cerebellum springs into action. It receives a copy of the motor plan from the cerebrum and receives a constant stream of sensory feedback from your body. Current position of your arms, the angle of your joints, your overall balance. The cerebellum compares the cerebrum's intended plan with your body's actual state. Is your hand moving too fast, too slow? Is it in the right position? As the ball gets closer, the cerebellum makes instantaneous, microsecond adjustments to the motor commands, smoothing out the movement of your arms, ensuring your hand arrives at the precise location at the precise time. Finally, the refined motor signals travel down your spinal cord and out through the peripheral nerves to the muscles in your arms, hands, fingers. These muscles receive the electrochemical messages and contract accordingly, positioning your hands perfectly. As the ball makes contact with your palm, sensory receptors in your skin send a new signal back to the brain, confirming the catch. In that brief moment, your eyes, cerebrum, cerebellum, spinal cord, nerves, and muscles all work together in a perfectly timed symphony of neural control and coordination. Finally, let us examine the very last step in this chain of command the moment a nerve's message becomes a physical action. The collaboration between nerves and muscles is where the brain's intention is ultimately translated into motion. Muscles contract or shorten only when they receive a specific instruction from a nerve. The point where a motor neuron connects to a muscle fiber is a highly specialized synapse known as the neuromuscular junction. This is the final handover point for the command signal that originated in the brain. It is the bridge between the electrical world of the nervous system and the mechanical world of the musculoskeletal system. When an electrical impulse from the brain travels down a motor neuron and arrives at the neuromuscular junction, it triggers the release of a specific neurotransmitter. This chemical messenger crosses the tiny gap and binds to receptors on the surface of the muscle fiber. This binding event initiates a chemical chain reaction within the muscle cell, causing it to contract and generate force. This force pulls on the tendons, which in turn pull on the bones, creating movement at the joints. Every single movement you make, from the powerful stride of a run to the delicate flutter of an eyelid, is the result of this precise and reliable process. It is important to distinguish between the two major types of muscles that nerves control. First, there are the voluntary muscles, also known as skeletal muscles. These are the muscles attached to your skeleton that you have conscious control over. When you decide to walk, write, or wave, your cerebrum is sending deliberate commands to these muscles. The pathway is clear. An idea forms in the brain, a plan is made, signals travel down the spinal cord, out through motor neurons, and into the specific muscles required to perform the action. This is the domain of willed, purposeful movement. In contrast, there are the involuntary muscles, also known as smooth muscles and cardiac muscle. You do not have conscious control over these. They are found in the walls of your internal organs, such as the stomach, intestines, and blood vessels, as well as in the heart itself. The nerves that control these muscles are part of an autonomic or automatic system, managed primarily by the brainstem. These nerves ensure that your heart keeps beating and your digestive system keeps working without you ever having to think about it. While both types of muscle rely on nerve signals to function, the source and nature of that control are fundamentally different. You have now journeyed through the intricate world of neural control and coordination. You have seen how our body receives messages. You have seen how those messages travel along a network of nerves. You have seen how our brain and spinal cord process them to create purposeful action. We have demystified the neuron. We have explained the life-saving speed of the reflex arc. We have explored the specialized roles of different brain regions. You can now trace the path of a signal from a sensory organ, then to the brain, and back out to a muscle, as illustrated by our story of catching a ball. With this foundation, the unseen conductor is no longer a complete mystery. The question we began with, whether you can move your hand without your brain, now has a clear answer. For a voluntary action like tapping a table, the answer is no. The command originates in the cerebrum. For a reflex action, the spinal cord can command movement before the brain is even aware. Understanding this distinction is key. The reward for this knowledge is a deeper appreciation for your own body and a powerful tool for learning. If you are studying this topic, I encourage you to use this knowledge actively. What is one habit you currently use to help you revise complex subjects like this? Please share it in the comments below. Your method might be the perfect solution for another learner. To make this knowledge truly your own, you must engage with it. Draw the neuron. Sketch the reflex arc. Explain the story of catching the ball to a friend. These simple acts of recall and application will move the information from short-term memory into long-term understanding. If this exploration has been helpful, please subscribe for more journeys into the wonders of biology. Share this guide with anyone who might find it useful. We'll pin the most helpful comment to the top of the discussion. Share your favorite tip from this essay, then reply to another comment with an additional tip. By building on each other's ideas, we can create a powerful resource for all. You now possess the core concepts of one of biology's most fascinating topics. You have the tools to understand how you perceive and interact with the world. You have learned that the seamless link between feeling and moving is the work of a silent, brilliant, and perfectly coordinated system. Keep practicing, keep questioning, and you will master it. Subscribe, drop your best revision habit in the comments, and share this with a friend who's revising neural control. I'll pin the most helpful comment, add your favorite tip, and reply to someone else's with another. Let's build smarter together.